Okay, so I guess we can start talking about impedance. It's like, so as I mentioned before, it's a topic that I just have to say a lot of words about, and then hopefully something will make sense about it in the end. Impedance is resistance. It's kind of resistance that you see from the practical standpoint of building circuits. Most of the time, other classes use resistance as the word for this quantity. Impedance includes the complex value. That's the only difference. It includes something called reactance. For all practical purposes, it's resistance. In this class, we'll use it essentially like resistance. What matters is in this class, we're going to build circuit components that are meant to be kind of self-contained. In other words, you can pull out, like what I've drawn up here, what's in the dots there, you can pull that out and look at it as a component, as a black box, and then have it work well with other parts. Now, just by the very nature of some resistances affect other resistances, that's where impedance is important. You always want to have high input impedance and low output impedance. It's kind of like, it's one of those things that you just have to remember and then keep coming back to that. Let me write that.
So the reason I'm confused about that is because in the quiz that we did,
Right.
It was the opposite. With the potentiometer.
Right. Let me find the paper for that.
I have it if you need.
Okay.
So this was like the 10 to 1 rule.
Yeah, this is where that comes in. So what did the quiz look like? Phase one volume control. This is a typical Tom problem because he gives you one of the values as the load. Okay. Yeah, so this part, there's two black boxes, one on either side. One is the load and one is the power supply, and you're going to figure out what goes in between. You guys know how to find output and input impedance, kind of what the difference is and how to see them? Okay. I guess we can start with that because it's pretty, on voltage dividers, it's the easiest to explain it, but you can apply kind of the same idea to all of them. So I'm just going to put some arbitrary values up here. Here's the input. Here's the output. That's a voltage divider. It might as well be, something with 6 resistors, anything like that. The way you figure it out is the input impedance is the total impedance going through the circuit down to ground. Almost all these circuits are going to have ground of some sort. If they don't have ground, then it's an infinite input impedance because you never complete the circuit. In this case, since out is just a hanging wire, you treat it as a hanging wire for figuring out input impedance. So essentially ignore this part of the circuit. It's just the total impedance down to ground, which in this case, 2 resistors in series, so it comes out to 2K. So I'll write that there. R in equals 2K. Output impedance is kind of the more confusing of the two. There's a lot of ways they try to explain it. I think the notes say it's something like the resistance when you short the output to. It's not a very good way of explaining it. Basically, what you want to do is you want to do the same thing as input impedance, except you're looking from where the output is back through the circuit, and you're treating the input as a ground essentially. I have to be kind of careful with how I say that, but for practical purposes, that's a way to think of it. It's not technically, you don't ground the input, you short the output. There's a confusing kind of difference in how they word it. Just pretend you're from the output looking back through the circuit, and what's the overall impedance you see there. So in that case, it's just from the output looking in. You have 1K, 1K, this time they're in parallel, so it's 0.5K. I'll write that there real quick. So this is where the 10 times rule comes in, is where your output impedance, let me make sure I say this right. Basically, you want high input impedance and you want low output impedance. So the output impedance has to be 10 times smaller than your next input impedance. So in the case of the quiz problem, you'll notice that in this case, RIN, just by the way the voltage divider is designed, it's higher than ROUT. Good design is generally you want to do that. This is the example in the second to last page of the day one notes. So if you look at that one, this one, it's the exact same as that, so you can go back through and figure out the impedances. This will get to the quiz problem very quickly, but stage one, this is A. The input impedance is 8K, so it's got a pretty high input impedance. That doesn't matter because there's nothing coming in from the other side. The output impedance of this, if we just look at this segment, is 2K, because same thing in parallel. So our out A is 2K. What that means is if you were doing kind of this sort of this setup, and you wanted, let's just say arbitrarily you have 5 volts up here, you want to make sure that with this divider, you're going to get 2.5 volts right here. That's the design of this divider. Essentially, by making sure you match the output impedances, you can design this circuit and say, this circuit is going to give you a 2.5 volts out. And no matter what you put on this side, that's not going to affect it. This is kind of what you're seeing in lab, where let's say, instead of connecting it to this next part of the circuit, let's say you attached it and you said, all right, perfect. It's a 2.5 volt source. I'm going to run my 4K load with it and see what happens with that. Just put a 4K load right there. Well, what's going to happen, you can already kind of see it, is this 2.5 volts isn't going to be 2.5 volts. It's going to sag a little bit. That's because you have 4K and 4K in parallel now. This component's input impedance is 4K just because it's a single component. And since your output impedance from here originally was 2K, 4K is not 10 times bigger than that. So in other words, this is going to affect the previous component. Good design is you design, let's say the output impedance of this, you want low output impedance. Let's say the output impedance was 100 ohms. If it were 100 ohms, then this input impedance of 4K is plenty higher than that, and there wouldn't be a problem. It's one of those things that when you see it happening kind of on the board, it makes a lot of sense. For now, just remember low output, high input impedance is the goal. So in this circuit, the original one, the original one here, if you're thinking to yourself, I've got this divider, the output impedance is 2K, I need the input impedance of the next stage to be at least 10 times that, and I want to do a voltage divider. In that case, you just pick 10K and 10K because that's 20K in total. So the input impedance here is RN is 20K, 10 times bigger than 2K, it works. You can do the exact same thing over here, same math. The output impedance of this is 10 and 10, so it's 5K, and then input is 50 there. Looking at the quiz problem. First off, is that making some sense here? Hopefully. All right. Potentiometer gives the amplitude of the signal sent to a load, which might be. When I took this class, I think on the final we had a problem a little similar to this. It was one of the earlier problems, so this is like something that looks a little bit familiar. Okay, so there's 2 stages. I'm gonna erase all this and put this up there real quick. You have the most important part is your load is high input impedance from the look of it. It's just drawn as a resistor. What that means is you need to have low output impedance for your middle stage, but you also want it to be higher than that first stage. Okay. Cool. Drawing your missing component. So right here, the only kind of the most important part to keep in mind is you want your output impedance of that stage right here to never go higher than 10K. You hear a lot of times they'll say worst case. Worst case is your since you want a high input impedance, a really low input impedance, or a really high output impedance. So yeah, let me read the description at the very bottom. that, by the way?
Whenever you can.
Since you're adjusting the volume control, it's going to be some sort of potentiometer dongle thing, which is what I put up there. In this case, this is going to be at least 100K. The worst case for the input impedance is going to be 100K, so we can just treat that like that. Therefore, this one, you want a minimum of 10K for your, let me make sure I'm saying that right. The highest output impedance you can get is 10K. You can always go lower than that. It's going to slightly affect this value because they don't specify this value. They say you can, choose it however you want. Is the solution you had on there? Did you say that was right? Okay. Because sometimes there's other factors that
Yeah.
show up for some reason. So yeah, what you did there, 10K. Just looking at this component, the input impedance of this. So we want to do all the worst cases. So worst case, Rn, we want Rn to be high. So what's the lowest Rn you can get? Well, Rn, if it just goes, if you have the wiper all the way up, it's going to go straight through. Your Rn is just going to be 0. Make sure I'm doing that right. Oh wait, sorry, because that's floating. So Rn's always going to be 10K, I bet. Because this part wouldn't, it would be floating for Rn. So Rn of 10K, it's going to just always be 10K. And remember, the way we get Rn is to treat the output as a, not connected to anything. So this is the highest, lowest Rn. And in fact, it's always Rn. The Rout, in this case, can range anywhere from, if the potentiometer is all the way down here, then the Rout is 0. If it's all the way out here, the Rout is going to be 0 as well. The worst case Rout is going to be when it's in the middle of this 10K resistor. So it's a little abstract to think of, but then the 10K resistor just becomes two 5K resistors. Since you're right in the middle of it, the two 5K resistors, so 2.5K is the total Rout in that case. Anything other than that should be lower than it. So 2.5K out, that just means the choice of 10K resistor works here, but you're leaving a little extra room, so it's okay. 2.5K versus 100K, the factor of 10 is satisfied by quite a bit there. You could actually take that resistor all the way up to a 40K. Because with a 40K resistor, you'd have 20K and 20K, and then you split the middle, it would be 10K, and the worst case RO would still be lower than 100K. It's correct to use 10K. It's just, you can use up to 40K just because of the nature of how you calculate RO. What 10K does do though, is since your input impedance for 10K ohms, that means this value your output impedance per unit stage has to be 1K ohms. So it limits a little bit there, but not, significantly. Yeah.
Okay, I think the problem is I was thinking of it as your output, say in the middle, is going to feed your input on the next component.
And the next one, yeah. You always want to think, compare this output to this one's input. It's easy to say, but making that actual mental connection is a little bit tougher. Yeah. I guess the weirdest part is the fact that the 10K output impedance is 2.5K, just because if you think of it up here, it's 0. If you think of it down here, it's 0. So if you pick in the middle.
Right.
Yeah.
Okay, but so your output in that middle guy is not equal to the input in your next, because your next one is a completely separate box, right?
Right. So as long as you satisfy that condition, they don't affect each other.
Okay.
Yeah.
Cool.
Yep. So going with, did the problem ask you to pick a value for this one too, or?
Yeah.
Yeah. So that would just be,
Same with you.
in this case, it'd be 1K.
Yeah.
If you pick 40, you could do 4K.
Okay. I see. Thank you.
So that's impedance in that part of the circuit. By the way, I think we're officially scheduled for 3 to 6, but since there's not that much, if you guys want to, I was going to plan to finish a little earlier than 6. You guys didn't want to stay that whole time. Okay. Is there anything else from the class notes or from the homework that was particularly like not explained well? I have a couple of topics here just to.
From day one?
Either one, yeah. One that I can talk on a little bit while you guys look through. This class does electricity, and two components of that traditionally are voltage and current. One thing that's kind of useful to know beforehand is we're going to talk about current very, very little in this class. Almost all of the signal processing, almost all of the homework problems, anytime you're moving information through a circuit, it's almost always going to be voltage. The only times I can think of there where current is kind of more relevant than just kind of that background thing. When we do transistors, which will be in about a week, current is kind of, it's a very big component of how they work, but in the way that kind of Tom teaches it, in the way that this class teaches it, you don't have to kind of really think too much about the current. So it's there, but you don't have to focus on it. The other thing is when we get to op amps and a couple other circuits, there'll be a concept of how much can an op amp drive. Now the op amp is a small component, it can only output so much current, and that's relevant because in some cases, you want to hook the output of the op amp to a high power thing and need a lot of current through it, but the op amp can only source like 25 milliamps or something. So I guess current in that area is only really just making sure you don't overexert a part for the max current that it can output. Other than that, everything else is voltage.
One thing that I'm still confused on is the notion of load.
Yeah, load. It's I gotta find a different way to explain it because it's one of those things that after a long enough time you just kind of accept it, and that's how I kind of came to understand it. A load is just very often in electronics, your power source isn't a perfect power source. Where you're getting kind of your voltage input into a system has a bunch involved in within it. And when you put a load on there, in ideal electronic design, you want to be able to put any load on there and not affect kind of what's supplying the voltage. In other words, if I have this voltage divider outputting, let's say there's 10 volts on top, so I'm outputting 5 volts. I want to be able to attach that to, in a perfect world, 100 ohms and have it still be 5 volts and get however many amps that is. I'd be able to attach to 100K and still get that same 5 volts. Why? So load is just anything you attach to a component where you want to keep the voltage constant, but the load might distort that voltage. So we're working in the lab there. Basically, you want that third resistor to be able to have 5 volts to it or whatever the value was without it depending on what the value of the resistor was. It all comes back to impedance, I guess. That way, loading happens when you don't do the 10 times rule between the impedances. And loading is generally bad. That it kind of inhibits the modularity of the system when you have to kind of worry about, what's the output impedance of the last stage or what stuff like that.
Okay.
So, yeah, later on when we get to op amps, everything's a little bit easier. You generally just want to make your input impedance as high as possible, and you want to make your output impedance as low as you can. Let's see what else there is. You guys understood a lot of that stuff with filters, with high pass, low pass, F3dB, and all that stuff, or should I talk on that?
Well, it was kind of hard to understand why it's killing the.
Oh, for the differentiator and the integrator? Yeah, let me see if I want to draw this one up there where I can just talk on it. Essentially, so the capacitor passes through the difference, right? The capacitor, when you move a sine wave through, you get a cosine on the other side because you're moving the difference, you're getting the differential. When you pass kind of a higher signal through that, let me find that page actually. Somewhere in the middle of class 2. right between pages 6 and 7. The part that I'm looking at. So why does it kill the signal? That's the question. You know, this is one of those things that with the notes that we have, it's kind of, I'm sure there's a physics explanation for it, but I'm trying to, I remember a point last year, I remember figuring out the reason for this. So I'm gonna, I think this is the explanation, but it's not a very satisfactory explanation. The way the capacitor works is by, there's that equation relating the current to the change in voltage, right? The current through the capacitor is equal to constant times dV dt. What's happening essentially is with just moving that current, the current doesn't accumulate enough voltage on the other side. It's physicsy the reason why that's the case. But the fact that you have the current moving and the current allows some charge to accumulate on the capacitor, but before very much is accumulated, you're moving back and forth and back and forth. That's the reason. Kind of to simplify things, we usually say, oh, you know, you're passing through the difference in voltage to the other side of the capacitor, and that's true, in the sense that you're passing the current on the other side is proportional to the difference in voltage, and the current eventually accumulates that voltage. The problem is the current doesn't accumulate enough voltage to the same amplitude as what you put in. I hope it's kind of, you know, that's, if you look at the equation, the I equals C dV dt, just throw it up there. The I is the current on the other side of the capacitor, and what that current essentially does is it's starting to, you know, fill the capacitor. It's adding electrons to the capacitor, increasing the voltage on the capacitor. That's dependent on the change in the dV dt. The thing is, dV dt, this value is also swinging back and forth with your input signal, and it's the current that's changing. Nowhere in here does it say voltage on the capacitor. So in other words, what you're passing through isn't the voltage, it isn't the perfect, you know, isn't the differential of voltage. You're passing through a current that is proportional to the change in voltage. That current then kind of accumulates charge on the capacitor, and that creates that voltage. So in other words, I guess where you're losing it is the current isn't enough to get it up to the original voltage level. So it's kind of a very deep physics-based kind of answer. But.
So it's still separate planes, separate.
Yeah.
And there's no.
You're going to get into the discussion that is a question that gets asked every year is, what is AC current and how does AC current actually work? Which it's complicated, but yeah, I'm not going to try to explain it unless I can try, but you just have to trust that when you have DC current makes sense. You know, electrons are moving one way. When you have there was an old analogy that I heard a long time, not the water pipe analogy, because everyone's heard that one. But this, I don't know if this will help. I'll say it just to kind of get it out there. But if you've ever pedaled a bike and you're pedaling with both feet, that's sort of DC. You're constantly pushing forward to, you know, push things through the system. AC is kind of like you're pedaling your bike, but now you only have one foot to pedal your bike. So you're pushing on the first part, and then you're pulling. You kind of, you know, wrap it behind the pedal, pull it on the way back, push it. You're still moving current through the system. The current isn't necessarily, you know, one direction through, but you're getting current through the system just the same. You're just pushing and pulling that. For practical purposes, the current is still moving through the system. One of them, you're going one direction, it's the DC, you have both feet pedaling. For AC, you're still pushing and pulling, but current's still moving through the system. So maybe that helps to understand it, maybe that confuses it more. I thought it was a pretty good analogy. And that's why it can seemingly go through the capacitors, is because when you're if you think about the current when you're pushing and pulling, you're kind of adding to one side, adding to the other side of the capacitor. That's how the current flows through the system. The capacitor still effectively acts as a short. In other words, there's no current moving through it, but there's current moving around it in such a way that you can come to see it in a way that, it's moving through it. Cool. Any other things that were, let's see, integrators, differentiators? I can say just kind of in general for where the course is going for the next little while, because it's always good to get a forecast of what's coming up. This week is, I believe, still kind of simpler things. I think we do diodes. Thursday, Friday might be transistors. I don't know if it starts that, or if it's not this Thursday, Friday, it would be next week's Tuesday, Wednesday. Transistors are hard, but you don't have to, they're hard because they are hard, but we try our best in this class to try to make it kind of memorize these, and if you memorize these and use these, the rest of the picture will start to fill in a little bit more. Once we get to those, that'll be fun for whoever does office hours that week, because transistors are a little bit tougher. I guess the reason why they're hard is because you have to keep in mind this affects, there's 3 terminals, but each terminal needs to have a certain condition. So I'm just going to say words, you don't have to remember any of this. The base voltage always has to be 0.3 higher than the emitter voltage. The collector, always has to have a resistor to kind of set the current. There's a lot of things to just keep in mind. All the rules are sort of set down and make sense, but there's just several you need to keep in mind at once, and that's why it's difficult. But after working with it enough, it becomes easier over time. Eventually we hit op-amps, and op-amps are, I think, 4 or 5 weeks of op-amps, and those are a lot nicer to use. Has the first PSET been posted yet, or is that still coming? I think Sawhill's doing next week's PSET. So yeah, the PSETs they don't take that long. They take a fair amount of time.
Okay.
Like you would look at them and say, oh, I can do this in 3-4 hours. It's just not meant to be the hard part. So. Yep. What else? Just trying to think of any other general things that are useful to know or relevant here. Oh, so capacitors. I can talk about capacitors because that's something that is relevant beyond just the high pass, low pass differentiator integrator. You're going to want to use decoupling capacitors a lot. The reason for that is what happened. Basically, a capacitor holds some charge on there, and when you have a little extra charge on there, and there's an aberration from the norm, the power supply flips or something draws a lot of current at once, the extra charge just sort of helps save that. So if you ever get a waveform that is just a little bit too fuzzy, like you can see where the line should be, but there's a lot of fuzz around it. Plug in a decoupling cap. There's a little ceramic, little circle clay dot looking things. Those are really useful. Blocking capacitors are also a topic that I don't think Tom talks about them that much in lecture if they come up, and that's essentially where we've learned that the capacitor takes the differential of what's coming into it. So if you have a signal that's varying and you want to knock out any DC component, in other words, you only want to change, you can just put a capacitor right in the way. Typically, you want to use a pretty big capacitor for that. And the reason for that is it's better blocking. It's in the notes somewhere.
Wait, can you say that again? So if you have like DC.
So let's say for some reason you have a signal coming in, and it's sine wave centered at 5 volts.
Okay, so does that mean AC necessarily or no?
In this class, it just kind of the word is always signal. AC technically is anything that changes, back and forth, and DC is anything that's constant.
Right.
Most of the signals will be sort of mixed. They'll, I guess technically you'd call them AC, because they do have that alternating component, but they might be shifted, you know, this goes up to maybe 6 and 4, something like that.
Okay.
But if you put this through a decoupling cap, so just more circuit on the right side, you assume, and then they would, you know, drop down to centered around 0. So decoupling caps knock out the DC component. That helps in some cases where you want a signal centered around 0. There's a couple of problems that use that. Probably on the first homework would be a problem like that.
So that kind of reminds me, I also don't understand the idea of this introducing a DC offset, like a bias offset.
Right.
Yeah.
Yeah, that's usually the reason for that. I guess the reason you use that is if you want to take a raw electrical signal and use it to kind of control something else. So say there's a thermostat that, depending on what value you give it between 0 volts and 5 volts, it decides how hot it's going to blow the air. And you have a signal coming in that's somewhere between, you know, +1 and -1 volts.
Oh, okay.
So you want to, you want to amplify it up until 2.5 on either side, and then you want to shift it up 2.5.
Okay, that makes sense.
So something like that.
Thank you.
There's a lot of, I'll bet you the midterm will probably have problems like that. It seems to come up. Yeah, there's a midterm at some point. Yeah, I just don't worry too much about those. Those are like, by the time you get there, you know a lot of this stuff. And you get a group sheet if they do it the same way. You get 1 page of as many circuits as you can fit on it. Yeah. I really hope we're doing that the same way this year. I'd feel awful if I told you guys that and it turned out it wasn't.
Well, now it's just up to you to convince them.
Yeah, I'm gonna make sure you guys get that. No, I'm pretty sure you'll like keep that because it's very, very useful.
Yeah, it's a lot of stuff to remember.
Yeah. Cool. Let's see.
So what's a good value for that?
For the decoupling cap, kind of usually in the labs when they tell you to use one, they'll give you a value. I'd say 0.1 microfarad or something. It's rough. It doesn't have to be anything particular, or even 1 microfarad. Do you guys know where the secret cabinets are? So if you guys ever are missing a part for some reason in those little bins, this is where kind of the library of all the extra parts are. So you usually just come over here and grab one. That's something people usually figure out like the last 3 weeks or so. But if you're ever missing a component, it's there. You just have to find it. Cool. I was gonna shoot to be done by 4, so we got 15 more minutes if there's anything you guys can think of.
Would you be opposed if I stayed just to work on stuff?
Oh sure, no, yeah, go ahead. That would be no problem. We're technically until 5 or 6, I think. So yeah.
I mean, I don't want to keep you like so.
Oh, it's okay. No, I'll just hang out here, and I have to. Well, there's a MIT career fair coming up tomorrow,
Okay.
and so I have to prepare a bunch of stuff for that.
Nice.
Yeah.
Are you graduating this semester, or are you graduating?
No, I'm just trying to get a job.
Oh, okay.
Yeah, for the summer or something.
Okay.
But, yeah. Let me see. I think because I remember when I took this class, there were things I didn't understand, but there's so many damn notes that you
Yeah.
never remember where they are. So I'm gonna try my best to be as helpful as I can. Find anything. You guys understand why we use decibels and kind of how those work? I remember that being weird to me the first time I did it. Because decibels are basically a logarithmic scale that is terribly difficult to understand, but like once you just kind of memorize how stupid it is, you understand it. Every 20 decibels is a factor of 10. And F3dB is where you drop 1/√2, which is, I guess, where we officially call a signal attenuated, is when it drops that percentage. There's a section on phasor diagrams in your notes. Don't read that. It'll confuse you more, and it's not, like, without the proper math for it, it's just kind of extraneous. So you can skip over that part.
Will it show up afterwards?
Never shows up. In fact, Sahil and I joke about it a lot because it's the word that we drop every single class, and people are like, "Oh, that's going to be a legit physics concept," and then we don't actually go into it at all. What it is essentially is you're using the complex plane to represent phase, and you can add signals using that. Basically, using the imaginary component as an offset to add signals, and it just becomes a little bit not that necessary.
Because kind of confusing
Yeah, the explanation in here is just 4 pages too short.
without knowing the definite difference of impedance and
Yeah,
resistance, I guess.
yeah. Just treat impedance as resistance, and when there's a capacitor, just memorize the fact that the impedance of it goes up. Let me make sure I do this right. It goes down with frequency, so higher frequencies move through a capacitor more easily. And what was the other dependence? I have it on my computer. One other tip I have for this class is there's not that many equations involved, but when there are equations, make sure you write them down and star them, because very often problems will just be, oh, plug it into that equation, and it's not a hard, it's maybe 2 things multiplied divided by a third.